Dear friends, welcome back. So, let us now proceed to solve a weight estimation subroutine, where we will take up again an example problem with some data, like we will not get into that how you are going to get the historical data here, but we will consider that as an input for this example, and then we will try to develop a subroutine which helps us to figure out what should be the weight of the UAV without not exactly going into the aerodynamic details of the configuration. So, once you have the weight of the UAV, then you can think of designing a wing and selecting an aerofoil. So, that follows this weight estimation. So, to start with, we need to know how to estimate the weight. So, this weight estimation actually requires power requirement, like as an input, what should be the power, typical power requirement by the system, which we have already solved for cruise, takeoff as well as climb performance, right. So, that was the reason why we have initially handled those three examples or developed those three subroutines. So, let us now proceed to solve this weight estimation problem. So, the example here is, estimate the weight of a UAV, the weight of a UAV which has to carry out a surveillance mission for 2 hours, carrying or with a EO IR payload that weighs about 1 kg. So, at a cruise at a flight velocity of 30 meters per second, the UAV is powered with an electric brushless motor and propeller combination with a propulsive efficiency .92, right, comma, motor efficiency 0.95. Let us change this 0.92 of 0.95 of propeller efficiency and motor efficiency of 0.9 and electrical efficiency of 0.98, right. Assume the lift to drag ratio during the flight is 15, right. So, consider the following data. Following data of a baseline UAV to estimate the weight of the current UAV. Okay. So, given propulsive efficiency, so what we have is, structural weight ratio, right. So, this is W. W structure upon total weight of the aircraft is given as 0.4 from the baseline aircraft. So, propulsive W of propulsion unit or brushless motor upon weight of the total weight of the UAV was given as 0.15, and yeah, electrical efficiency is 0.98 and motor efficiency 0.9, and then propeller efficiency or propulsive efficiency is 0.95. Okay. So, what exactly is it mean? And again let us put down all the data that was given. So, we need to carry out emission requirement, right. So, from the question we need to estimate the weight of a UAV which has to carry out a mission of surveillance mission for 2 hours. That means, it has to, the time of flight has to be minimum of 2 hours. Let us assume, let us now estimate the weight of the UAV only for this 2 hours plus for takeoff and then returning to the base. So, that we are not accounting here. What we will do is, what should be the minimum weight of the UAV in order to carry out this 2 hours mission, 2 hour surveillance mission. So, the time required is 2 hours here. Okay. And also the SED, specific energy density, that we have to consider for a battery is 100 watts watt hour per kg. Okay. So, this is the specific energy density that is considered. So, the time of flight is 2 hours and the velocity of flight should be 30 meters per second, and L by D during flight is given as 15. So, instead of just fixing this 15, again let us try to iterate this from, say, from 10 with a step of 1 up to 15. Okay. So, this is what we are going to do, or say 17 as well, that is up to you. So, we can iterate this, we can make this as a variable as well as. So, this is from the mission requirement. So, we can't change this much. So, 2 hours of flight is also a mission requirement here, and the another data that we have from here is payload weight, right. So, W payload is given directly, right. So, it is given as 1 kg, right. So, this is what the data we have from the given question. Now, let us look at the typical architecture of this brushless motor propulsion. So, what we have is similar to that of IC engine, we have shaft power as an output from a brushless motor, right. Let us assume this is my brushless motor. Okay. So, the output from this brushless motor is shaft power PS, right. When I connect this, when I connect a propeller to this shaft, so what I achieve is power available, or the useful power for the UAV to make it, to help it, to help the, like this power available will help the UAV to move forward, right. Okay. Let us see what exactly this shaft is connected to. So, this shaft inside is connected to a armature, right, which is positioned in between permanent magnets, right. You can say multiple permanent magnets in most of the cases. So, say there will be a bearing here through which this shaft will be out, right, and then the end of the shaft again is connected to. So, to the other, like opposite end of this motor. So, say this is this is another bearing through which this shaft is mounted. So, it is like a simply supported setup here. It is grounded at two ends of it, and then this armature rotates inside this particular motor, which is having what you call coaxial permanent magnets, right. So, now, so the reason for me to consider this is like the input for this motor is electricity, am I correct or not, P electric, right. So, the input for the motor is P electric and the output from this motor is shaft power. So, the electrical efficiency or say the motor efficiency here MOT is equals to, so output from this motor is Ps upon P electrical, right. So, this is the output from this motor, and then this motor again is connected to a speed controller here, what we call it as electric speed controller. So, this is ESC. Okay. And then it is again connected to finally to the power source, right. So, the power source that we carry is a battery here, lithium LiPo battery. Okay. So, say this is your LiPo battery. Okay. So, and from here, so this is the power from the battery, right. So, the power from the battery PB. Okay. So, the PB is the input for this electrical connections, that includes ESC and all other wiring here. So, when there is a power supply through this electrical equipment, there is resistance, of course, we can't avoid resistance. So, there is certain losses here, right. So, that electrical efficiency is given as, so the input for this electrical efficiency is power from the battery BAT, otherwise you can consider this power from the battery, and the output is power electrical to the motor, which is input to the motor here. So, P electric upon P battery is the electrical efficiency and it is given as 0.98, right, and motor efficiency is given as 0.9, and we have like the useful aerodynamic power here, or the power that is useful for the UAV to move forward is PA, right. So, that is the output from the shaft power, right. So, where from the propeller. So, the propulsive efficiency is the input output upon input. So, output is power available upon shaft power PSH or PS. Okay. So, now if I have to talk about what is the overall power available, if I have to relate this power available and power battery power, what I need to do is, so power at the battery that I require is equals to BAT is equals to power electric upon propulsive efficiency, right, eta electric. So, this is equals to, so what is P electric? Again I can convert this P electric from here, right, it's PS upon P motor, right. So, 1 upon eta electric 1 upon eta motor, so times PS here. So, again I can convert this PS as PA upon 1 upon eta propulsion times PA power available. So, whatever the power available from the system should be equal to the power requirement at that particular flight velocity, is not it? That is what this power available should do. If I should set the throttle of the motor in such a way that the combination of this motor with the propeller should deliver the required power by the system to perform that particular mission, which is surveillance mission here, right, at a particular velocity and L by D. So, if this power, so the power required for that particular flight condition, when it is satisfied with this power available from the motor, then it will be able to fly at that constant velocity of 30 meters per second. Okay. So, finally, if I have to understand what should be the weight of the battery, I need to first understand what should be the power requirement of this entire system, or the power that has to be supplied from the battery, right. So, how long I should supply this power? So, it is mentioned, right, 2 hours here, let us say. Okay. So, this power from the battery, okay. So, energy at the battery otherwise. So, we can't talk in terms of power there, right. So, energy energy required at battery, right, is equals to power required or power at the battery, power that need to be delivered by the battery times the total duration of flight or delta t. Okay. So, this is what will help us to know what is the energy required by the battery. Now, once you know what is energy required by the battery, by using the definition of specific energy density, right. So, what is specific energy density? Specific energy density is the amount of energy stored in a battery per kg, right. So, that is watt hour per kg, weight of the battery, weight of battery. Why we are calculating this? That will be the only variable here, is not it? I will show you that. So, weight of the battery is specific energy required by the battery or energy required from the battery upon to carry out that particular mission upon specific energy density. So, if you have energy in watt hour, then you divide it by watt hour per kg, what you have is a weight of the battery in kg. Okay. So, that is what WB, this is equals to W battery. So, what is the total weight of the aircraft? Weight of the aircraft is, this we have already derived, no, in our previous course. Please refer to that video, the video link will be given below. So, please refer to that. So, the weight of the aircraft is structural weight plus propulsive weight, weight of the propulsion system plus weight of the battery plus assuming all other accessories, weight of all other accessories, that is for a particular system is already included in this, right. So, structure plus propulsion plus battery plus payload for a UAV. Okay. So, payload weight is given directly in kg. So, we do not have structural weight as such. So, what we need to do is, this is given as the ratio W STR, right. W STR upon W is given, this structural weight ratio is given times the total weight plus propulsion weight upon total weight is a propulsion weight ratio times the total weight of the aircraft plus weight of the battery is not given, which is unknown, that we need to find out. So, it varies from mission to mission, is not it? That is very clear here. If it is delta T changes, the battery weight changes here, because battery weight, again this battery weight is equals to P bat times power that is need to be delivered from the battery times delta T upon SED, specific energy density. So, this power at the battery depends upon this power available. So, it depends upon the flight conditions as well. So, from one mission to the other mission, the overall power requirement changes. So, if you are flying at different velocity, this power available, that the power that need to be made available from the power plant to the system changes, right. So, at the same time, when you are flying at a different L/D, you have different power requirement altogether. Okay. So, the current approach that we are going to adapt is not a generic approach. So, this is what I generally use and found to be very useful in designing a UAV. So, there can be many other approaches. I am not generalizing and stating that this is the only approach that is available. So, the steps that we need to follow here is approach, what we will be doing. So, consider the weight and ratios of baseline UAV. Okay. Now, so what are we doing here? So, this battery weight, so payload weight is fixed, payload, this is fixed. So, this is what is changing, is not it, that the battery weight has to change, and it depends upon the initial weight as well, initial weight of the aircraft as well. So, with the initial weight for a different mission requirement. So, the initial weight was given from the baseline aircraft, right, is not it, here it is from the baseline aircraft. So, considering that weight and estimating it for a different altogether a different mission, right, will also affect the initial weight itself at the end of this mission, because the battery weight may not be same as the battery weight of the previous UAV, which was considered as 4 kgs, right. That was the baseline UAV that we considered. That may not be the battery weight that for this particular mission may not stay within that limit. So, in that 4 kg maybe say about 1.5 kg is the battery weight for to carry out a mission that was like that UAV was designed for. But the current UAV has to perform a different mission altogether, which is a 2 hours surveillance, right. So, for that case, that 1.5 kg of battery which you have considered earlier, for that case the 1.5 kg battery that was assumed for the total weight of the aircraft, which was about 4 kg, may not be suitable for this particular mission requirement. That is the reason why we are trying to estimate with that initial weight, assuming that is the initial weight, what is the overall weight of the battery that we need to carry here. Now, with that battery we will try to update this W, right. So, that iteration continues until we achieve convergence between 2 consecutive iterations, right. So, let us say, so I plus 1 minus Wi, so the error between them, if it is less than 10 power say some value. So, then we will say that okay, what we have achieved is a kind of convergence, right. So, and the weight estimation is more or less a decent value, right, it gives us a decent value here. So, for that what we have to do is, so first one is consider the initial weights and then try to iterate for the convergence, because the battery weight changes, that means the overall weight changes. So, with that overall weight figure out what is the power requirement. So, initial guess weight, so or say initial weight from historical database. So, this is from historical database. So, with this initial weight and for that particular mission requirement, right, for mission requirement, okay, estimate what should be the battery weight, right, thereby estimate what should be the weight of UAV. So, let us say Wn is the new weight of the UAV, Wi is the initial weight that is considered. So, if this initial new weight and the initial weight, if they are same, one and the same, that means whatever you guessed as the initial weight earlier or whatever you have considered the initial weight will also is good enough to satisfy this particular mission requirement, which means this new weight again is the structural weight, right, of the new UAV times the propulsive weight of the new UAV and then the battery weight of the new UAV plus the payload here. Okay. So, here these weights are updated based upon this new weight here. Okay. Got it? So, if this new weight and the previous weight, if they turn out to be same in the previous iteration, if they let us say if there is an error, then this iteration continues, like the power requirement for this with the updated weight. So, the new weight will become the what you call input of this iteration. Let us say if I iterate in this within this loop, then the new weight will now become the initial weight and then we will try to estimate what is the power requirement with this new weight, right, to carry out that particular mission, thereby estimating the battery weight, and then from that battery weight again we will find out what is the total weight of the UAV. Right. So, within this loop we will not update the structural weight and propulsion weight. So, they are defined outside the loop itself. Okay. So, within the loop we are not doing that. So, once we achieve this, then we will try to update those structural weight and propulsion weight and then again repeat, because when you update them again the total weight changes and then repeat this exercise. So, that we are more or less close to this particular weight estimation of a new UAV, right. Okay. So, it will be easy as we start writing the code. Okay. Let us start the new subroutine. So, as usual I am clearing the database, I am clearing the memory and closing all the windows, say if they are open. So, yeah, or say I would like to consider the velocity as input, velocity of flight as an input here. So, input enter the flight velocity. Okay. So, velocity in meters per second. So, at the same time I would also like to have total time of flight as an input. So, into the total time of flight in hours. So, after considering these two as an input, so from the given data, so the baseline aircraft, so the weight of the baseline aircraft is also given here. So, which I forgot to mention, is given as 4 kg. Okay. This was the weight of the baseline aircraft. So, this 4 kg includes everything. That was an earlier aircraft we were asked to consider to start like estimating the weight of the current UAV. This may not be for 2 hours mission requirement like surveillance and L by D at 15 and then velocity at 30 meters per second, right. So, that may not be exactly same. So, but we will consider that those details here. So, whatever it was given is, so baseline aircraft weight is given as 4 kg. Okay. So, and structural weight ratio WST underscores W, right, that is a structural weight ratio which is given as 0.4. This is structural weight ratio, which is WST underscore W, or say W structural upon total weight of the aircraft, right. So, and then the propulsion weight ratio is given W underscore, so PRO, rest W pro underscore W is 0.15. This is propulsion weight ratio. And then, so the L by D of flight we are going to vary, right. So, okay. So, for what are we doing? L underscore D, let us say that as L by D of flight is varying from say 10 with an increment of 1 till 15 or say 16 otherwise. Okay. So, you can control this limits of this for loop. Okay. So, while varying this, what we need to do is, so for each and every time you need to start with 4, right, whether it is L by D 11 or L by D 12 or L by D 13 or L by D 15. So, the baseline aircraft details are same, one and the same, right, is not it. So, for that what I will try to do here is the structural weight ratio before entering into the slope, I would like to give them as an input here. Okay. So, that is structural weight ratio W underscore STR, cap underscore STR is the structural weight itself, which is W STR underscore W, that is structural weight ratio times W here. Okay. So, this is in kg. So, we are dealing in kg right now. So, and then W underscore propulsion weight ratio PRO, capital letters So, this is weight of the propulsion system, weight of the structure weight of the UAV, structural weight of the UAV. So, the propulsion weight is total weight is equals to propulsion weight ratio PRO underscore W times the total weight. So, this gives me what is the structural weight and the propulsion weight here. So, that is outside the iterations, and then so I would like to use some variables for this iterations again, just to know as well as save the data. So, I is equals to 0, let us say I k is equals to 0 here. So, k is equals to k plus 1 here. So, this will talk about L by D. So, k corresponds to the variable of iterations in for L by D here. So, I just want to save this L by D, or say let us say this variation is small l d. Here I am storing it as capital L D of k comma 1. It stores in a vector column vector is equals to L underscore D, L by D, or say capital L by D here, capital L by D. So, now the initial weight of the UAV, I would like to assign this Wi, the initial weight for this iterations, as the weight of the baseline aircraft W. Okay. So, that is the weight of the UAV, and then I would like to have another variable which is W. So, W, okay, which is 0. I am just assigning it just to start, like as I told you, I want to compare this. Let us say W is the final weight after the iteration, each iteration. So, Wi minus W I would like to compare this should be less than, or so otherwise say should be greater than 10 power minus 10, right. If it is greater than 10 power minus 10, this loop runs. Okay. So, the error, so this loop will break as soon as the error with the initial weight of the iteration and the final weight after that iteration. If it is, if the error is less than 10 power minus 10, so it will break, otherwise it will keep running. Okay. So, what I am trying to do here, so Wi is considered as W every time inside the, even inside the iteration. So, Wi is equals to W, because I need to upgrade this Wi, right, is not it. So, the initial weight I am considering is a baseline aircraft weight, but inside that loop, after each and every loop, this Wi has to be upgraded here. So, this you will understand once we complete this program. So, yeah, I is again, so Wi is not related with this I, don't get confused with it. So, I am I plus 1 talks about the iterations progress here, and then Wi is W, and what I have to calculate is power required, right. So, that was the whole idea there. So, if you look at here, I need to calculate the power required, and I need to make sure that that is available, power available here, is not it. So, apart from this, there are efficiency, so input data related to propulsive efficiency, motor efficiency, and electrical efficiency. So, efficiency underscore PR, propulsive efficiency, is equals to 0.95. So, efficiency underscore battery is equals to propulsion, efficiency underscore propulsion battery, and then what you have, electrical, ELE, electrical efficiency. So, let us say this is also PRO. Okay. So, electrical and I am sorry, this should be motor efficiency, okay, MOT, motor efficiency, brushless motor efficiency, which is 0.9 and electrical efficiency is 0.98, right. Okay. Yeah. So, the whole idea is since we have this as an input here, once I know what is the power that I need to deliver from the battery for this particular mission requirement, and it is very clear that if I know that battery power required, I will know what is the battery weight. So, I can update this battery weight and get the new weight here, is not it? Okay. That is what I am trying to do here. So, because efficiencies are given as an input here, so what I need to know is power available, which should be power required to perform that particular mission. Okay. So, that is what I am trying to do, power required by the system, which is nothing but the power available in our case. So, power required each and every time is equals to weight of the aircraft, right, weight of the aircraft Wi times. So, this is in kg, I am just converting it to newtons. So, L upon what is the power required here? So, for a level flight condition. So, this is like a surveillance mission at a L by D, constant L by D, right. So, that means more or less a level flight here. So, L is equals to W, right, and T is equals to D are the governing equations. So, the power required for us from these two equations is like thrust required times velocity of flight, is not it. So, that is nothing but drag times V infinity, or say if you divide these two equations, if you divide, so otherwise power required is thrust required times velocity of flight. So, divide these two equations, what you have is thrust required upon W, T by W is equals to D by L, or say thrust required is W upon L by D. So, we are not exactly going into the details, aerodynamic details of this. Instead, we are considering this L by D is available. So, for if you want to have this much of weight for your UAV, then you need to make sure that you fly at that particular L by D. So, you have to design your wing to deliver that particular L by D. So, L by D from here will be used as an input for your wing design, right. So, L by D W times V infinity is from the mission requirements upon L by D is your power required here. So, I am not explicitly calculating each and every variable here, like thrust required and then power required, the way we performed earlier. Instead, I will just use this. So, this is like W times G, which is like in newtons, weight in newtons, and then what I have is velocity of flight, which is input from here. So, that is V upon L by D, right. So, L by D is what? This is my L by D. So, okay. So, now I got power required. So, can I calculate what is the battery weight? Am I correct? Or power required at the battery? So, power required at the battery is 1 upon electrical, 1 upon motor efficiency, 1 upon propulsion efficiency times this power required here. So, let us say P bat, P, this is capital P underscore bat, battery, power that need to be delivered at the battery is equals to, okay. So, what is this? This is equals to power required 1 upon, so I can say 1 upon efficiency, EFF efficiency of propeller multiplied by efficiency of motor multiplied by electrical efficiency. Multiplied by, so power required PR. Okay. So, you now got to know power at the battery, power required at the battery. So, can I say what is battery weight? WB, W underscore battery weight. So, W underscore battery, right, BAT, capital B. So, inside the iterations, let us W underscore battery is equals to power underscore battery times the time of flight, right. Where is time of flight? T. T is the time of flight in hours, right. So, divided by specific energy density. So, we need to give SED also as an input in watt-hour per kg. So, say control C, SED specific energy density, enter the total specific energy of the battery in watt hour per kg. Okay. So, now you got weight of the battery. So, with this weight, so without actually using this, no, we consider them the structural weight and propulsion weight as a constant inside, otherwise we will not be able to achieve a closed form solution here, right. So, W of the total aircraft, now the new weight of the aircraft is now W, assuming the structure still remains same, structural weight plus W underscore propulsion system weight, because the propulsion system can deliver a variety of power, is not it, right. It is not considered only for single power. So, assuming this power requirement is still satisfied by this, and the structural changes because of just increase in the battery weight is not much. Okay. So, and then what we have is the new battery weight, that is BAT here. This is the new battery weight, right. So, now actually W is getting updated with this new battery weight, plus payload is already given. So, payload was not considered here, but it was given as an input. So, let us write W payload. Okay. So, W underscore PL, let us say, is a payload weight, which is equals to 1 kg, right. So, W payload is, so, payload of EO slash IR sensor in kg. Okay. Directly the payload was given. So, PL talks about payload. So, what you are going to achieve is W is in kgs, because everything else is in kgs here. Okay. So, for calculating power we need to convert that weight in from kgs to newtons, because we are expecting power in newtons, because velocity is in meter per second, and so we need to convert that again. So, for calculating power required, we need to convert this weight to newtons instead of kgs, because we are expecting power required in watts, right. Okay. So, now we got the weight W. Now, what I want to do is, so this W minus Wi, Wi is the initial weight that I have considered. So, what I am trying to do is, I am assigning this WW as W, right. After, otherwise you can say WF, you can consider this as WF for this loop, WF, and then say WF. W is the final weight that is estimated after this particular iteration, each and every iteration, which is equals to W here, right. That is the final weight. Now, difference of this initial weight that I have considered and the final weight, let us say if they are, if it is very less, if it is 10 power minus 10, let us say. So, then this loop will break, saying that whatever the battery weight that you have estimated for this particular endurance is already satisfied for that 4 kg, right. Otherwise, this will keep iterating. No? This is one convergence approach that we have used. So, this will end this first while loop, right. And now, since the weight is increased, the structure weight as well as propulsion weight need to be upgraded. Earlier these structural weight and propulsion weight, since the battery weight is increased, the total weight also increased. So, but these two at line 22 and 23, the structural weight and propulsion weight we considered is from the weight of the baseline UAV, not the current upgraded UAV, right. So, once this iteration completes, then we will try to upgrade this and then also again repeat the same procedure to find out what is the total increase or the change in the weight of the battery, thereby finding out the overall weight of the UAV. So, now again let us say this has to be for the same L by D, right. So, what I will do is I will just copy paste these things here again same, including the entire. You can either make it as a function, that will make more sense, but just want to copy paste this again. So, the second iteration here is the structural weight is now the same structural weight ratio, we still have the same structural ratio, but the new W. So, the new W is this one after this initial iterations. So, initially in this particular loop what we have upgraded is just the battery weight, right. So, that means the total weight of the aircraft is upgraded from in terms of battery. Now, what we are doing is with that battery weight we are upgrading structural weight and propulsion weight system. So, that these are the two weights that we are upgrading for the new UAV for the new mission requirements, right. And once we complete this task, then again when there is an increase in structural weight and propulsion weight, there should be an increase in the power requirement to perform that. That means again the battery weight has to be changed. So, that means again in the second iteration, so this battery weight will be changed. So, while considering this upgradation, you can take a factor of safety, so that this particular battery weight will be satisfied within that limit. The increase in the weight will not affect the propulsion weight increment as well as structural weight increment. So, we will end this after 2 iterations here. Okay. In general, what I observed is like after these 2 iterations the weights are more or less within the estimates, limits of the estimates. So, I will end this program. Finally, the weight that I am going to get here is otherwise is the end of this particular. So, for each loop, for each L by D it ends after these 2 while loops, right. So, that means the final weight of the battery or the final weight of the UAV W of otherwise what should say V underscore final for that particular L by D, that means I, which is k comma 1, right. So, which is k comma 1 here is equals to W that I am going to get here or WF whatever it is, that is stored, and then weight of the battery is also stored, weight of the BATT battery after this 2 while loops is k comma 1 is also stored for each and every L by D, this keeps varying, right. So, this weight of the battery is here W underscore bat that you are going to get here, and then weight of the battery propulsion system. What will be the weight of the propulsion system? So, once you know the power requirement for each and every flight envelope, you can select a power plant and you can get the precise power requirement weight. So, this is an initial estimate to start the design process. So, once you have precise weights, once you select the power plant based upon the power requirement, you will get to know. You can again come back to this loop and then iterate this and finalize the battery, because in that case more or less you have another fixed variable here, is not it. So, the same motor which can deliver 23 k say jet engine or a small brushless motor which can generate 10 kgs of thrust can also generate 5 kgs of thrust, right, the same motor. So, yeah, with that understanding we are not upgrading these structural weight, propulsion weight inside the loop itself. So, this is the battery weight that we are storing, and then the propulsion weight is what W pro. Okay. So, propulsion weight, battery weight, and then payload is given. So, the total weight is also given. So, apart from this, what do we require? Yeah, we do not require anything. So, with L by D, how this W final is changing as well as battery is changing propulsion. So, if you want to plot, you can plot a figure. So, figure 1, I can have subplot plot plot L by D, L underscore D, right, where is that, L underscore D. So, each and every time let us say this is W B is the baseline, W underscore B. So, this will become W underscore B, otherwise it will be an issue. So, from here once you get W, so that will automatically be changed here, right. So, let us assume for the initial iteration it will be always for different L by D you have to start with the same baseline aircraft, right. So, let it be W underscore B, otherwise it will be upgraded no, with the new weight every time. L by D, and where is this L by D here, it is a column vector L by D, yeah, with with L by D how this W underscore final weight is changing. Y label syntax, okay. So, it is W, right, let me just put W underscore total weight, right. So, maybe it is worth mentioning kg, okay, total weight in kg, total weight in kg. L by D varying with W, how the battery weight is varying, BA, let me just copy this. BAT, battery weight, TOT, total, let's not write the entire thing, total. So, we are also plotting the propulsion weight variation with battery weight. Okay, so x level is L upon D. So, let us see if this works. So, we have not saved this yet. So, weight estimation. So, we are estimating the weight of the UAV only for say that particular mission, you know, only for that cruise. We are not estimating for say if there is any extra or with a factor of safety, as well as we are not considering the takeoff and climbing flight as well as landing flight. Right. Yeah. So, here in the first while loop, so since we have updated this as W base weight W underscore B instead of W, if there is no for loop then it will not be an issue, but since we are iterating for L by D here. So, for different L by D how this weight of the aircraft is changing. So, what I did is I used a if loop here. So, if I is equals to is equals if I is 1 like this variable of this loop is 1, then that is at the initial iteration. So, this W I is nothing but W B, right. So, else if for any other thing, so this W I will take W weight of the new weight that we have estimated, right. So, and then it will find out what is the error between them, and if the error is less than that, it will break and it will continue with the next iteration, next for loop, next while loop here with the upgraded structural weight and propulsion weight, right. So, here it will not be a problem, because what we want is the new estimated weight should be the input to this particular while loop, which is happening here. So, the only difference that makes is this if loop, with that too because we have a for loop here, right. We are iterating it for L by D. So, another upgrade is that I would also like to plot this structural weight, how it is varying with L by D, right. And then I have made it as a subplot of 4 by 1 right. So there are 4 rows which talks about these 4 subplots with final weight, battery weight, propulsion weight and structure weight varying with L by D here. So, let us figure out. So, the flight velocity is 30 meters per second and then duration of flight is 2 hours from the data, and the structural SED says specific energy density of the battery or energy density of the battery. Actually, it should be specific energy density. Okay, I missed it. Please, I'll make a correction. Right. So, if this is the case, so we have a plot here. So, see the structural weight in kg is so it has to be 13 when L by D is 11, and then it can be as low as 2.3 when you have L by D of 16 here. So, yeah, see the propulsion weight ratio is almost close to 8.5, 850 grams. You have, so with that propulsion, and the battery weight is close to say 3.2 kg when you have L by D 16, right. For the same flight conditions, when L by D is varying, overall weight turns out to be 7.3 kg, right. So, when the L by D is say 11, see the structure weight increases to 3.5 kg, and then the propulsion weight you will be carrying is about 1.3 kg. So, with the battery weight and is as high as 10 kg, you need to carry close to carry a battery which weighs about 10 kg here just to perform that mission, and then the overall total weight of the aircraft turns out to be about 16 kgs here. So, see this helps us to helps us to understand the significance of L by D in the flight performance, right. So, as the performance increases with the L by D, you require less battery weight, less structural weight, and overall weight will also turn out to be comparatively less here, right. So, this is just an attempt to start with the weight estimation. You can say preliminary weight estimation, that you can start with this code, and then once you have the detailed weights, you can further complicate this algorithm. I wish you should extend this program for even takeoff and based upon the mission requirement, whether it is a hand launch UAV or say it has a typical takeoff and landing capability. So, then based upon that you need to, and then the climb, right. So, what is the climb that you are expecting, what is the altitude of cruise. So, based upon those parameters, I wish you should upgrade this code to estimate the overall weight of the battery as well as the UAV depending upon a baseline aircraft. So, this baseline aircraft we do not have much time to discuss. So, that is from the historical database. I leave it to you to figure out, to study, at least study various textbooks and figure out what are the baseline, like how do we extract this historical database from those from the previous UAVs, right. Okay. So, in the next lecture we will talk about wing sizing based upon this weight estimation and the L by D that we have considered. What should be various combinations of, like say, or what should be the wing planform geometries as well as the cross sectional profile geometries, okay, or say parameters. Okay, then see you. Thank you.